So in this video, we're going to play a game to see how well Professor Stewart can manage the little bit of screen he's got. What I want you to see from this video is trends in how these orbitals fill. Now what we're trying to build up to is why the periodic table is the way it is. So you've spent a lot of videos now going through quantum numbers. You understand what these 4s, 3p's, 3s, 1s all stand for. Let's talk about why the periodic table is arranged the way it is. So let's start with something very simple. Let's start with electron filling diagram. Now I told you in a previous video how to fill it up based on the number of electrons, but let's take a simple treatment here. Let's actually make an atom with a number of electrons. What we want is a neutral atom. So for an atom to be neutral, the number of protons and the number of electrons have to be equal. So if we have something like hydrogen, okay, hydrogen we have one proton, so for it to be a neutral hydrogen atom we had to have one electron. So if we want to do the electron filling diagram for hydrogen, we would just have this. If we had 2 electrons, we'd be up to helium, so we'd have this. Now hydrogen was the first atom we talked about. It has the lowest number of electrons for a neutral atom, and it starts out above that first column. Now helium's a weird one, and we'll get to the end of the video why it's a weird one. Let's go up to the 2s now. So we need 3 electrons to get to the 2s, and this is going to correspond to lithium. So now we've got lithium with 3 electrons and beryllium with 4 electrons. So this is filling lithium and beryllium. Now we start filling up the 2p orbitals. So we need 5, 6, 7, 8, 9, 10 electrons. So these are atoms with 1 and 2 electrons. These are ones with 3 and 4. And this is 5 to 10 electrons for the neutral atom. And what we see as we're filling up through here is boron through neon atoms. Now we get to the 3s. We're back to the 3s. We've got sodium and magnesium. So this is 11 and 12 electrons. We're back to the first 2 columns. You notice that? When we're filling up the 1s and the 2s, we're in the first 2 columns of elements. When we fill up the 3s, we're in the first 2 columns of elements. But when we fill up the p, suddenly we're on the right side of the periodic table. We're in those right 6 columns that stand out above the fatty center of the periodic table. So what happens when we go to the 3p? Well, when we're at the 3p, we're at 13 through 18 electrons. And these will be elements like aluminum, all the way through argon. So as we're filling up our p orbitals, we're once again back into that tall set of columns that are on the far right side of the periodic table, aluminum through argon. Now we're back to 19, 20 electrons. In this case, we're filling up potassium and calcium. So as we're filling up these s orbitals, once again we're into the first 2 columns of the periodic table. Now we're getting to the d's. Now before we went between the first 2 columns, the last 6 columns, first 2 columns, and the last 6 columns. Now we need an element with 21 electrons. So this is going to be 21, and to fill up all 21 we need 2 electrons, so this goes to element 30. So this is going to be scandium to zinc. And you notice we're no longer filling up p electrons here. What we're doing is we're filling up d orbitals, and these d orbitals are now being filled up as we move through those elements that are in the center of the periodic table. So what's the next orbital up? Well, this is going to be our 4p. And as we fill up our 4p, we're going from gallium to krypton. And this is 31 to 36 electrons. So once again, as we're starting to fill up our p orbitals, we're back to those far right side of the periodic table. We're filling up those last 6 columns. So when we look at the periodic table, okay, it's not arranged arbitrarily. The first 2 columns are elements that are filling up s orbitals with their highest energy electrons. So if you look at something like lithium beryllium, the first 2 electrons in lithium and beryllium are the 1s, but their highest energy electrons, the 2 valence electrons, the ones in highest energy, are all in the s. And this is true for sodium magnesium. Sodium magnesium have 2p, 2s, and 1s electrons, but the highest energy ones are in the s orbitals. And this is true for potassium and calcium, and so forth. When we are dealing with elements that are filling up their p orbitals, we're dealing with the last 6 columns of the periodic table. And we'll always see that's true. We have our 3p's, we're filling up aluminum through argon. We have our 4p's, we're filling up gallium through krypton. 5d's will be indium through zinc. 6p will be thallium through radon. When we start filling up d orbitals, we're in the center of the periodic table. So scandium through zinc, yttrium through silver and lanthanum through mercury. Those are elements that are filling up their d electrons. What about the f orbitals? Well, if we could continue drawing on this diagram, what we find out is that when we get to element 58, cerium, that's when we start filling up the f orbitals. So the periodic table is arranged in such a way that we're not representing it, we're representing it a lot of different ways, but one of the major ways we're representing it is by where the highest energy electrons are located, specifically the symmetry of those orbitals. And this is going to play a huge role when we start trying to figure out how electrons are transferred between elements, because based on where they are in the periodic table will dictate how many orbitals we have to work with. So let's say we work with something like carbon. Carbon has 6 electrons, so we're back down here. Just erase these orbitals up here. We work with carbon. We have this configuration. So too many electrons there. But what you can see is the p orbitals aren't completely filled. So something like carbon can accept up to 4 electrons and still have its p orbitals filled. We don't have to go to a higher energy orbital because it's already got electrons in the p level. And so this is why we break the periodic table up the way we do. What we want to do is we want to group elements based on how the electrons are filling, because the electrons are going to be the major players when it comes to figuring out chemical bonding, how many electrons are typically gained or lost during reactions, everything like that. So now you know, looking at the periodic table, why we have the regions we have.